Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through idempotent and nilpotent matrices. So you may have come across the terms idempotent and nilpotent in other areas of maths, say group theory. They mean the same thing here. We're just applying them to matrices. So these are very good topics to study because they will consolidate your understanding of other things you learn in linear algebra. So let's start with what it means for a matrix to be nilpotent. So an n by n matrix A is nilpotent if there exists a positive integer k such that a to the power of k equals 0. Of course, when I say 0 here, I mean the 0 matrix. So A necessarily needs to be square because we're talking about raising a matrix to a power, and you can only raise square matrices to a power. So we're basically saying here that a matrix is nilpotent if one of its powers is equal to the 0 matrix. And the way matrix multiplication works is that any subsequent power will also be equal to 0. So if a to the power of k equals the 0 matrix, then so too a to the power of k plus 1 and a to the power of k plus 2, a to the power of k plus 3, and so on, they will also equal the 0 matrix. So now we'll take a quick look at the idea of the index of nilpotence. So if we know that a to the power of some integer is equal to the 0 matrix, there must be a smallest such integer. So the index of nilpotence is the smallest positive integer, k, such that a to the power of k equals the 0 matrix. Now, very interestingly, it turns out k is always less than or equal to n. Remember, A was an n by n matrix. So if we have, say, a 4 by 4 matrix, the index of nilpotence of any nilpotent 4 by 4 matrix must be less than or equal to 4. If we're talking 2 by 2 matrices, for example, that means that if a 2 by 2 matrix is nilpotent, then A squared must be equal to 0. So note, the 0 matrix is the only matrix with an index of nilpotence equal to 1. And that should be very easy to see. So let's look at some examples of nilpotent matrices. Let's look at each of these 5 matrices on the screen, and we'll go through and see which, if any, are nilpotent. Now, when we're talking about nilpotent matrices, people always assume that the matrix has to have lots and lots of zeros inside, but that may not be the case. In fact, it's not easy at all just to look at a matrix and tell whether or not it is nilpotent. So it turns out here that A is nilpotent, but B isn't, even though they look the same. Now that's just because in B, the non-zero element is on the diagonal, the leading diagonal, so it will be multiplied by itself when you square B. So in fact, B squared is equal to B. But A, if you square it, you will get the 0 matrix. So people would probably look at B and think, oh yeah, it must be nilpotent. Actually, it's not. So C is actually nilpotent no matter which value of A that you choose. So the index of nilpotence for A and C is both 2, as I said. If the square of a 2 by 2 matrix is not the 0 matrix, then it's not nilpotent. If a 2 by 2 matrix is nilpotent, it must have an index of nilpotence of 2, unless it is the 0 matrix. So let's look at D. Well, D gives us some insight into looking at a matrix and determining whether or not it's nilpotent. It turns out that any triangular matrix whose diagonal entries are all 0 is nilpotent. So this is a lower triangular matrix, but the diagonal entries are 0, so it is definitely nilpotent. It turns out that D squared doesn't equal the 0 matrix, but D to the power of 3 does. So the index of nilpotence of D is equal to 3. Now let's look at E. E actually has no entries that are equal to 0, but it turns out that it is actually nilpotent. It has an index of nilpotence of 2 because E squared is equal to the 0 matrix. So the method we used on D wouldn't work here on E because E is not a triangular matrix. But it turns out you can rule out matrices from being nilpotent straight away by checking their trace. So it turns out that all of the eigenvalues of a nilpotent matrix are equal to 0. Remember, the trace of a matrix is equal to the sum of the eigenvalues. Therefore, the trace of any nilpotent matrix must be equal to 0. And you can see A, C, D, and E all have a trace that is equal to 0. Unfortunately, this only helps us rule out matrices. So if the trace of a matrix is not equal to 0, the matrix is not nilpotent. But if the trace of a matrix is equal to 0, that doesn't say anything about whether or not it is nilpotent. It may or may not be. So if the matrix you have is small, you can tell definitively whether or not it is an idempotent matrix, not just by looking at it, but you can keep multiplying the matrix by itself and see if you end up getting the 0 matrix. For small matrices and some slightly larger ones, if you're using a computer, check its eigenvalues. A matrix is nilpotent if and only if all of its eigenvalues are equal to 0. So now we're just going to do a quick proof involving nilpotent matrices. So the proposition we're now going to prove is that if a matrix is nilpotent, then it can't be invertible. So to prove this, we start by letting A be an n by n matrix. So in shorthand, I write R n by n. We're going to let its index of nilpotence be k. So that means A to the power of k is equal to the 0 matrix, but A to the power of any number less than k, like k minus 1, is of course not going to be equal to 0. And I guess I should specify here that k is a natural number. It's one of the positive integers. So here we're actually trying to prove a negative. We're trying to prove that the matrix is not invertible. So usually the easiest way to do that is reductio ad absurdum, or if you like, proof by contradiction. We're going to assume that A is invertible, knowing that it's nilpotent, and then show that that gives us a contradiction. So we assume that A is invertible. It actually doesn't matter whether or not A is invertible for this next line. It turns out A to the power of k is just A times by itself k times. So because of the associative property of matrix multiplication, I can put the brackets wherever I like. So I can put them here. So what I have is A to the power of k equals A times, now this set here will have k minus 1 A's. So it'll be A times A to the power of k minus 1. Of course, you probably already knew this identity. I just wanted to show you that it works for matrices as well as for numbers. But hang on a second. A to the power of k is 0. So I can write 0 equals A times A to the power of k minus 1. So this is a good sign because the proof involves what we know about A, and we've got A by itself here. So because A is invertible, that means, of course, that A inverse exists. So I can take this equation down here and pre-multiply each side by A inverse. So A inverse times the 0 matrix just is the 0 matrix. A inverse times A just equals I, the identity. But when you times the identity by another matrix, you just get that matrix. It doesn't change it. So I've got 0 equals A to the power of k minus 1. This is clearly a contradiction. And the reason it's a contradiction, because I defined it such that a to the power of k minus 1 does not equal 0. So what this is essentially saying is that if you have a matrix that is both nilpotent and invertible, there won't be a smallest integer that you can raise a2 to get 0. There won't be an index of nilpotence. And that, of course, is silly. If a matrix raised to a power is equal to 0, there must be a smallest such number for which that is true. So we've shown that if a matrix is nilpotent, then if it's invertible, that gives us a contradiction. So we can conclude that if a matrix is nilpotent, then it is not invertible. So let's go now and look at idempotent matrices. So a matrix is said to be idempotent if you square it, you get the same matrix that you started with. So the square of that matrix is equal to itself. Once again, we're talking about powers of matrices, so an idempotent matrix necessarily needs to be a square matrix. So you're probably familiar with some idempotent matrices. The zero matrix, as well as being nilpotent, is also idempotent, because if you raise it to any power, you get the zero matrix. Of course, the identity matrix of any dimension will always be idempotent. But once again, you can't always tell just by looking at a matrix whether or not it will be idempotent. It turns out that this third matrix here is also idempotent, but it's pretty easy to check whether or not a matrix is idempotent. You just multiply it by itself and see if you get the same matrix. So as we'll see in the lessons, it turns out that if a matrix is idempotent, all its eigenvalues are either zeros or ones. So now we're just going to do a quick proof involving idempotency. So it turns out that if a matrix A is idempotent, then any positive integer power of that matrix is equal to the original matrix. So to prove this, we're going to use mathematical induction. Turns out this is a very simple proof though. So A is idempotent. We know that A squared is equal to A. Of course, A to the power of 1 would also equal A. In mathematical induction, what we do is we assume that the statement is true for a set of values. So let's assume that A to the power of n is equal to A for all values 1 is less than n is less than k. So now the inductive step, what we're going to do is show that if it's true for A to the power of n, then it's going to be true for A to the power of n plus 1. So note, A to the power of n plus 1 is equal to A to the power of n times A. But A to the power of n, we said, was A. So A to the power of n plus 1 is equal to A times A, which is equal to A squared, which is equal to A, because A is idempotent. So this worked because we assumed that A to the power of n is equal to A. So what we actually showed is that if this is true for A to the power of n equals A, then it will be true A to the power of n plus 1 is equal to A. So it was true for A squared and A to the power of 1. So if it's true for A squared equals A, then A to the power of 3 equals A. But if A to the power of 3 equals A, n is 3, then A to the power of 4 equals A. Then n is 4. So A to the power of 5 must equal A. And so on and so on. That's what mathematical induction is. It's like you have a whole stack of dominoes, and you've shown that if the first one falls, then all the rest of them will fall, and that's what we've done here. So we've proved by mathematical induction that if a matrix is idempotent, if A squared is equal to A, then A to the power of any positive integer will also equal A. Alright, I hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.